my YouTube viewers. It's Crystal here. In this video, what we're going to be discussing is the ANOVA, which is an analysis of variance and how it relates to regression. So I think that this is going to be a very interesting video for me, at least. And the reason why is because I've been studying machine learning and Python since 2020, and I've studied statistics around that time as well, and I've studied R off and on around that time, and I'm studying R a lot more now that I know I can write an R program in Google Colab. And in all these studies, this is the first that I've ever heard performing in ANOVA in a regression. And the reason why is because ANOVA is analysis of variance, and ANOVA is used for statistical hypothesis testing, where you can test more than two distributions or samples, and you check, I believe it is the means of those samples. And that's the difference between the ANOVA and the other hypothesis test, because the other hypothesis test, you can test one sample or maybe two samples, but the ANOVA, you can test more than two samples. But I'd always use the ANOVA for hypothesis testing, and it never occurred to me that you could actually use the ANOVA for regression. And the thing about regression is, when I began studying machine learning, I studied regression in machine learning. But regression was actually in statistics before it was in machine learning, because machine learning is a much newer science than regression. So now that you know a little bit about ANOVA and machine learning and regression, we're going to go ahead and discuss how ANOVA works in a regression model. So ANOVA in regression is the mathematical engine that tests whether predictors taken together or in subsets explain a significant amount of variance in the response. It does this by participating total variability into explained versus unexplained components and applying an F-test to judge whether the explained proportion is large enough to matter. So what we're going to do is we're going to do a demonstration in R of an ANOVA and regression nested model comparison. So the first thing that we're going to do is we're going to set our seed. And the reason why you set your seed is so every time you run the program, the variables will be initialized to the same value. So we're going to type set.seed brackets 1, and you can put any number that you want in the brackets. Now we're going to simulate the data. So n is 100, which is the number of samples. X1 is our norm. That's a randomly sampled normal distribution with 100 samples, a mean of 5, and a standard distribution of 2. And X2 is, again, a randomly sampled normal distribution with 100 samples, a mean of 10, and a standard distribution of 3. So we're going to say that the true model uses both predictors. So y becomes 3 plus 1.2 times x1 plus 0.8 times x2 plus our norm brackets n 0, 2. So that's randomly sampled normal distribution with 100 samples, a mean of 0, and a standard distribution of 2. And that adds a little bit of error to the model, or to the y variable. Okay, so now we're going to fit nested regression models. So you're going to have a model small becomes LM, that means linear model, brackets y tilde x1. So that's a simple model. And then model big becomes LM, that's linear model, brackets Y tilde x1 plus x2. So the small model only uses x1, and the large model uses x1 plus x2. So we're going to compare the models using the ANOVA. That's an analysis of variance. So you have ANOVA, bracket, small model, comma, big model. So that's something that's really interesting, because in the past when I studied NOVA, I also always just studied NOVA in regard to samples. So it would be ANOVA, sample 1, sample 2, sample 3. But in this instance, we're using ANOVA in comparison to models. So not only what that shows is not only can you use ANOVA for samples, you can also use ANOVA for models. So now we're going to plot the data. So plot brackets x2, comma, y, comma, PCH, that's the size of the dot, is 19. Color is steel blue. Main, that's your label, is relationship between y and x2. X lab is your x label, which is x2. Y lab is your label on your y-axis, which is y. And then we're going to put a regression line in the plot as well. So you've got AB line brackets LM, that's your linear model, brackets Y tilde x2, color is red, line length is 2. So we're going to look at our ANOVA. And on our ANOVA, you've got like your small model on row 1 and your large model on row 2. So your small model on row 1, you have a residual degree of freedom of 98, and then you've got a residual standard error of 900, and then you don't have anything after that. But on the large model, you have a residual degree of freedom of 97, and your residual standard error is 422. Your degree of freedom is 1. Your sum of squares is 477. Your F statistic is 109. And your p-value is a really low value of 1.28 to the negative 17. And then this is a printout of the relationship between y and x2. So you've got your regression line, and then you've got the samples, you've got the data points, and you can see the data points don't form any kind of a line, don't form any kind of a relationship to the regression lines. The samples are just sitting there amongst the regression line. So that's telling you that you have a lot of error. And so we come back here, and residual sum of squares, you can see that it's a lot of errors. And so basically, so you've got x2 goes from 4 to 16, and y goes from 10 to 25. And you can see that all of those lines, all those dots, are not really forming anything very close to the regression line. So you're not going to have a very high degree of accuracy, and you have a lot of error. Next thing we're going to talk about is post hoc tests. So post hoc tests are used after a significant ANOVA to determine which specific pairs differ while controlling the inflated false positive rate that comes from multiple comparisons. So we're going to do an ANOVA with post hoc comparisons. So the first thing that you want to do is you want to set your seed. And you set your seed so that every time you run the program, the variables are going to be initialized to the same value. So you type set.seed brackets 1, and you can put any number you want within the brackets. So now we're going to simulate data for 3 groups. And so a group is a factor, and we're going to create vectors for this. Brackets rep, it means like repetition. Bracket C means like combine. So it's going to be ABC, and each vector of being A, B, or C is going to have 30 elements in it. And so that's how we're going to create data for 3 groups. So we're going to calculate the true means, or define the true means. So mu becomes C brackets 10, 12, and 15. So that means the mean for A is 10, the mean for B is 12, and the mean for C is 15. So Y is our norm. That's a randomly sampled normal distribution with 90 samples, because in our 3 groups, you have 30 elements of each group. So 30 times 3 is 90. So you have 90 samples with a mean, with a repetition of the mu, which is 10, 12, and 15. And each equals 30, and standard deviation of 2. So then we're going to fit our regressive model with ANOVA is a regression with a factor. So model is LM, that's linear model, brackets, Y tilde group. And so your group is this factor that we've just created that has 3 vectors in it of 30 elements each, being A, B, or C. Now we're going to create an ANOVA table, and then we're going to do post hoc pairwise comparisons, and you're going to use a Tukey estimator, a 2P test to do that. So post hoc is Tukey HSD brackets AOV, that's analysis of variable, brackets model. So AOV is an ANOVA wrapper around a linear model for categorical predictors, and Tukey HSD performs pairwise comparisons of factor level means after ANOVA. So we run that all up, and you've got your ANOVA. So you've got your group and your residuals. So in the group, you've got a degree of freedom of 2, a sum of squares of 387, a mean square of 193, F value of 16, and a P value of 3.7 with the E negative 17. So that's a really low value. And then you've got your residuals, has a degree of freedom of 87, that's 90 minus 3, and the group degree of freedom is, you've got 3 groups, so that's 2 minus 1. And then your sum of squares is 279. Your mean squared is 3.2, and you don't have an F value or a P value. So Tukey multiple comparisons of means, 95% family-wise confidence level. And then so now we're going to calculate the model. So we're going to fit AOV, that's analysis of variance used within a linear model, and formula equals model. And then so you've got your how each vector, each group relates to each other, and you've got difference, lower, upper, and P adjusted. So all of the 3 P values are not very good. They're not higher than 0.05. So now we're going to talk about the F-test and how you calculate an F-test in a regression model. So the F-test in regression evaluates whether the regression model explains significantly more variance than a model with no predictors. The overall F-test compares a fitted regression model to an intercept-only model with no predictors. The hypotheses are: the null hypothesis is the intercept-only model fits as well as the regression model, and the alternate hypothesis is the regression model fits better. So we've got a little program here that we can use to demonstrate the F-test. So the first thing we're going to do is we're going to set our seed. So every time you run the program, the variables are going to be initialized to the same value. So you type set.seed brackets 1, and you can type any number you want within the brackets. And then we're going to simulate our data. So n, which is your number of samples, is 100. X, which is your independent variable, is R norm, which is a randomly sampled normal distribution with 100 samples, a mean of 5, and a standard deviation of 2. And your Y, which is your dependent variable, is 3 plus 1.5 times X plus R norm brackets, which is a randomly sampled normal distribution of 100 samples and a standard deviation of 2. And so Y is your dependent variable. Okay, so now we're going to fit our regression model. Model becomes LM, that's linear model, brackets Y tilde X. And then we're going to calculate a regression summary, which includes the F-test. So our formula is LM, that's linear model, brackets formula equals Y tilde X. Your residuals, you have a minimum, a first quartile, a median, a third quartile, and a max. You've got your coefficients for an intercept and an X variable. So you've got your estimate, you've got your standard error, you've got your t-value, letting you know that it's based on a t-distribution, and then you've got your p-value. And both the p-value for the intercept and the X are not very high. You've got your significant codes. So your residual standard error is 1.926 on 98 degrees of freedom. Your multiple R squared is 0.6639. Your adjusted R squared is 0.6605. Your F statistic is 1.93.6 on 1 and 98 degree of freedom. Your p-value is 2.2 to the negative 16. So that's a really low value. And then your value is 193. Your number of degrees of freedom is 1 because you've got two variables. You've got an X variable and a Y variable. Minus 1 is going to be 1. Your another degree of freedom is 98, and so that's going to be 100 samples minus 2 because you've got two variables, so that's going to be 98. And then you have a value of 6.12 to the negative 25th. So that's going to be not very high either. So next thing we're going to do is we're going to view our regression summary, and it includes F-test, and we've done that summary model. And then we're going to extract the F statistic, and degrees of freedom. So your F stat becomes summary model, F statistic, and then you've got your F statistic. See if we can find it here. So your F statistic is 6.123 to the negative 25. So that's a very low value. So we're going to compute the p-value manually from the f-statistic. So PF, f-stat 1, comma PF, comma f-stat 2, comma f-stat 3. So that's the f-statistic for the three vectors or the three groups, and lower dot tail equals false. So we've computed the p-value for the three groups. And now we're going to take the ANOVA table, and it's going to be the same as the F-test mathematically, and we're going to say ANOVA model. So the value of the F statistic for the three values is, I think, three groups, I think 6.12 to negative 25. So that's really low. So now we've got the ANOVA, which you've got your X and you've got your residuals. So you've got your degree of freedoms, and you've got your sum of squares, your mean squares, your F value, and your P value. So your degree of freedom for X is 1, and your degree of freedom for your residuals is 98. Your sum of squares for X is 717, and for the residuals is 363. Your mean squared for the X is 717, and for the residuals is 3.7. Your F value for X is 1.93, and it doesn't apply to the residuals, and your P value for X is 6.12 to the negative 25th. So that's a very low value. That's a very low value. So we're going to plot the regression model and F-test idea. We're going to compute a mean-only model, so that's going to be intercept only. So Y mean becomes the mean of Y. And then we're going to plot the data. So plot brackets X, comma, Y, comma, PCH equals 19, color equals steel blue, main is your title, is regression versus mean-only model, brackets F-test. Your label on your X-axis is X, and your label on your Y-axis is Y. We're going to add a regression line, AB line, brackets model, comma, color equals red, comma, line width equals 2. We're going to add a mean-only model line, so AB line, brackets H, that's for horizontal, equals white mean, color equals dark green, line width equals 2, LTY equals 2, and I think that means it's dashed line. We're going to add a legend. So legend brackets top is on the top left. The legend is going to be a vector of data regression line, mean only model. Your color is going to be steel blue, red, and dark green. Your PCH, that's the size of the dot, is going to be 19. LTY is going to be NA1, 2. So the regression line is going to be a straight line, and the mean only model is going to be dashed. LWD, I think that's her line width, that's going to be 2. So we've got the regression versus mean only model for your F-test idea. So your data is your blue dots, and you can see that it sort of forms a little bit of a approximation towards the regression line, but you still have a lot of error because the dots need to be as close to the regression line as possible. And you've got your regression line, which is red, and you've got your mean, which is just slightly more than 10. So that's what we calculated in this demonstration. So now what we're going to do is we're going to plot group means from a regression model. So you want to set your seed. So every time you run the program, the variables are going to be initialized to the same value. So you type set.seed brackets 1, and you can type any number you want within the brackets. So we're going to simulate data for the 3 groups, and this is the same as we did in the last program. Group becomes factor, brackets rep, that's a type of vector, brackets C, that's a vector having elements of A, B, C in it, and each vector is going to have 30 elements in it. So that's going to give you a total of 90 elements in this group. Mu is your mean, is going to be a vector of 10, 12, and 15. So A is going to have a mean of 10, B is going to have a mean of 12, and C is going to have a mean of 15. So Y is your dependent variable, is arc norm, that's a randomly sampled normal distribution of 90 samples, with the mean is going to be a vector of mu of 10, 12, and 15, and each is going to be 30. So that's going to be 30 elements in each vector, and standard deviation is 2. We're going to fit the regression model. So model becomes LM, that's linear model, brackets Y tilde group. We're going to extract fitted group means. So means becomes T apply, brackets, fitted, brackets, model, comma, group, comma, mean. So group is going to be either A, B, or C, and the mean is going to be the mean for that group. And then so we're going to extract standard errors for each group mean. So SE is your standard error, becomes summary, brackets, model, $ coefficients. We're going to be intercept equals group A mean. Other coefficients equals differences from A. So group means is going to be a vector of A is going to be standard error of intercept and estimate. B is going to be a standard error of intercept and estimate plus the standard error of group B estimate. And C is going to be a standard error of intercept and estimate plus a standard error of group C and estimate. And then so we're going to calculate our group means, and we're going to display them. And then standard errors for each mean. So group SE is going to be a vector of A. Looks like I've done that twice. No, I didn't do it twice. Of group standard error equals a vector of A is standard error of intercept and standard error. B of square root, bracket, standard error, intercept, and standard error squared plus standard error, group B, standard error squared. And C equals square root of brackets, standard error, intercept, and standard error squared plus standard error of group C, standard error squared. And now we're going to plot the raw data. So plot brackets S dot numeric group, comma, Y, comma, PCH, that's the size of the dot, is 19, color equals gray 60, XAXT equals N, XLab, which is your label on your X-axis, is group, YLab, which is the label on your Y-axis, is outcome. Your main is your group means from your regression model. That's your title. Your axis, brackets 1, comma, AT equals 1, colon, 3, comma, labels equals names, brackets, group means. Then you're going to add your group means, points, brackets, 1 to 3, comma, group means, comma, PCH equals 19, color equals red, CEX equals 1.5, and we're going to add error bars, plus or minus 1 SE. So arrows, brackets 1 to 3, comma, group means minus group SE, comma, 1 to 3, comma, group means plus group SE. Angle equals 90, code equals 3, length equals 0.1, color equals red, and line width equals 2. So you've got your group means being 10.16, 12.26, and 15.22. So that's very close to what we had defined it to be in the beginning of the program. And now we've got a chart of the group means. So your red dot is your group means. So for A, it's close to 10. For B, it's close to 12. And for C, it's close to 15. So now you can see that we've plotted the group means from the regression model. So now what we're going to do is we're going to talk about the ANOVA via the AOV. So the ANOVA via the AOV and regression via LM. So AOV is ANOVA in a linear regression model, and LM is a linear model with a factor predictor can be used to analyze a multi-group experiment. Both of these techniques can fit the same model, but just present the results differently. For a factor of k groups, the null hypothesis is all group means are equal, and for an alternate hypothesis, at least one group mean differs. So we're going to do an analysis of a multi-group experiment. We're going to simulate and load data. So what you're going to do is you're going to set your seed. So every time you run the program, you're going to initialize the variables to the same value. So you type set.seed brackets 1. So we're going to define our group, which is going to be a factor. It's going to be very similar to the groups that we defined in the two previous programs. Brackets rep, that's repetition. Brackets C, that means like combine. Brackets A, B, C, D, with each vector having 25 elements in it, giving you a total of 100 elements. So the means is going to be a vector that you're creating being 10, 12, 15, and 18. So the mean of A is 10, the mean of B is 12, the mean of C is 15, and the mean of D is 18. So we're going to define our Y variable, which is your dependent variable, is R norm, which is a randomly sampled normal distribution of 100 samples, with the mean being rep brackets means, H equals 25, and the standard deviation equals 2. So the mean is going to be the mean that's calculated in the group, being 10, 12, 15, or 18. And then so we're going to take this data, the groups and the Y variable, and we're going to convert it into a data frame. So data becomes data.frame brackets group, comma, Y. So group has 4 vectors in it, or 4 columns of data, and Y is 1 column of data. So you're going to fit the ANOVA model. So fit becomes AOV, that's an ANOVA within a linear model, brackets Y tilde group, comma, data equals data, and you're going to summary brackets fit. We're going to do a post hoc comparison in Tukey. So 2 key HSD brackets fit, because fit is what we have called the model, and we're going to plot the group means. So we're going to plot group, plot brackets group comma y. Main is your title, is a multi-group experiment. X lab is the label on the x-axis, is group. Y lab is the label on the y-axis, is outcome. And we're going to add mean points. So points, brackets 1 to 4, comma, T apply, brackets y, comma, group, comma, mean, comma, PCH, that's the size of the dot, is 19. Color equals red. CEX equals 1.5. And then we're going to calculate an alternative hypothesis with regression. So LM fit becomes LM, that's linear model, brackets Y, tilde group, comma, data equals data. So you've got ANOVA LM fit, and so that's going to be the same as your ANOVA table. And you've got your summary LM fit, which is the coefficients dummy coding. So there's actually two ways that you can do this model. You can do the model with a 2 key HSD, and you can do it with ANOVA, which I think is particularly interesting. And the reason why is because I personally had never heard of. I've been studying statistics and Python and machine learning and R since 2020, and I never heard that you could use an ANOVA in a linear model. So that's something that I found to be very interesting. So we're going to take the group and the residuals. So your degree of freedom is 3 because you've got 4 groups, and 4 minus 1 is 3. And the sum of squares is 901. The mean square is 300. The F value is 90. And your P value is 2 to the negative 16, which is really low. Your residuals are going to be 96 because that's 100 minus 4. Sum of squares is 318.1, and your mean square is 3.31. And then you've got your significant codes. You've got your two key multiple comparisons of means, a 95% family-wise confidence level. We're going to summarize the ANOVA model. So fit is AOV, that's ANOVA in a linear model. Brackets formula equals Y tilde group, comma, data equals data. And then you've got your differences, your lower, your upper, and your p-value adjusted for the different combinations of the group. And all of them are really low. So we've got the ANOVA model as well. So you've got, again, your degree of freedom, which is your group and your residuals, which is the same. You've got your sum of squares being 901 and 318. Your mean square being 300 and 3.31. Your F value being 90. And your P value is 6.55 to the negative 28, which is really low. And this is a summary of the model that we created. So it's linear model, brackets, formula equals Y tilde group, comma, data equals data. Residuals, you get your minimum, your first quartile, your mean in your third quartile, and your maximum. You've got your coefficients for intercept group B, C, and D. You've got your standard estimate, your error, your t-value, and your p-value. And you can see the p-values on all of those are really low. You've got your significant codes, and you have a residual standard error of 1.82 on 96 degrees of freedom. You get your 96 degrees of freedom because you have 100 elements in the data frame and 4 vectors in that data frame. So that's 100 times 4 is 96. You've got your multiple R squared is 0.7392. Your adjusted R squared is 0.731. Your F statistic is 90.69 on 3 and 96 degrees of freedom. And your p-value is 2.2 to the negative 16th. So that's really low level. So we've got this multiple group experiment. You can see here. So we've got the 4 groups. You've got the mean for A is 10. For B, looks like it's around 12. For C, around 15. And for D, around 18. So we've plotted this ANOVA. We plotted this for you. So the last thing we're going to do in this video is we're going to do a sample ANOVA report. And we're going to, again, simulate a 3-group experiment, which is very similar to what we have done in the previous programs that we discussed. So you're going to set the seed. So every time you set your seed, every time you run the program, it's going to initialize the variables to the same value. So you type set.seed brackets 1. You can put any number you want within the brackets. And then we're going to define our group, which is very similar to what we've done in the 3 previous programs. Factor brackets rep brackets C, which means you're going to create a vector with A, B, and C. And each vector has 20 elements in it. So that's going to give you a total of 60 elements. And then your means is we're going to create a vector of 10, 12, and 15. So A is going to have a mean of 10, B is going to have a mean of 12, and C is going to have a mean of 15. So we're going to define our Y variable, which is our dependent variable, meaning which is an R norm, which is a randomly sampled normal distribution of 60 samples. And the mean is going to be a vector of the means that we've just created. So each vector is going to be 3 vectors, and each vector is going to have 20 elements, and it's going to be the means of 10, 12, and 15, and the standard deviation is 2. Your DAT is you're going to create a data frame with this data in it. So DAT becomes data.frame brackets group, comma, Y. So that means you've got A, B, C, and then Y. You're going to create a one-way ANOVA for the regression model. Fit becomes AOV. AOV is an ANOVA in a linear model. Brackets Y tilde group, comma, data equals DAT. We're going to summarize the model that we created that we have called fit. Now we're going to perform some assumption tests. So we're going to plot brackets fit, comma, which equals 2. And so we're going to perform a QQ plot on that. We're going to do a homogeneity of variance test. So plot brackets fit, comma, which equals 1. So that's going to be residuals versus fitted. And we're going to do some post hoc test. So plot brackets fit, comma, which equals 1. Again, that's going to be residual versus fitted. And then we're going to plot the report. So the box plot, brackets Y tilde group, comma, data equals DAT. Main is your title, group differences in outcome. X lab is your label on your x-axis, is the group. Y lab is label on the y-axis is outcome. Column color is a vector with sky blue, light green, and salmon. So sky blue is going to be A, light green is going to be B, and salmon is going to be C. So we run the program. So we run the program. So you've got your group and then your residuals. You've got a degree of freedom of 2 for the group because you've got 3 vectors and 3 minus 1 is 2. You've got sum of squares of 249. A mean square is 124. Your F value, mean you're running it on an F distribution, is 41.56. And your P value is really low, being 7.38 to the negative 12. Your residuals, you've got a degree of freedom of 50 because you've got a total of 60 elements minus 3 vectors is 57. You've got a sum of squares of 170.9, and you've got a mean square of 3.0. Then you've got your significant codes. Then what we're going to look at, we created a QQ plot. So this is a QQ plot, and this is telling you that the data on the QQ plot very closely resembles a normal distribution. And so, yes, of course it's going to resemble a normal distribution because when we wrote the program, we wrote the program with R norm, and R norm is a randomly sampled normal distribution. So, yeah, the data points are going to fall in line with the normal distribution because we designed it that way. So we've got residuals versus fitted. So you've got your A, B, and C. So you can see your residuals versus fitted. And then you've got your group differences and outcome. So the group is going to be A, B, and C, and the outcome is going to be 16 to 18. So you've got your mean for group A is a little bit more than 10. Mean for group B is 12, and the mean for group C is around 15. So I think that concludes this video. And the next video, we're going to be talking about some more statistical topics in R. And I hope that you like it. I hope that you got something out of this video. I personally found it to be interesting because I personally didn't know that you could use ANOVA for a regression model and on a regression model. And all the studies that I've done for the past 6 years, I never came across anything like that before. So I certainly hope that you found this video of interest, and I'll be communicating with you in the next video.